All right, welcome back for part two of section 5.1. In this section, we're going to take that probability distribution idea that we've been looking at in section 5.1. So this guy right here, and we're going to say, hey, can you find the parameters of that distribution? That is, can you find the mean and the variance, and then from the variance, the standard deviation for that probability distribution? And the really cool thing about it is it's super simple to do. Right? So first off, remember that with the probability distribution, we are looking at a population and not a sample. Right? The reason this is a population is because when we set this thing up way up here, we found everything that could possibly happen. We didn't toss these coins 2 or 3 or 4 times. We said, here's everything. And anytime it's everything, it's a population. So since it's a population and not a sample, when we calculate the mean and the standard deviation from this, they are going to be parameters, not statistics. Right? Having said that, having gotten that out of the way, it's pretty straightforward. I got a formula here that says the mean, that is the arithmetic mean, the mu, since it's a population parameter, is the sum of x times p of x. Okay, now just to review a little bit, that guy right there, that's the sum symbol. So that means we're going to add up everything. Over here on the right, we've got x multiplied by p of x. So that's going to be like the number 0 times its probability, right? Or the number 1 times its probability. Or the number 2 multiplied by its probability. And then once we get all these values, we're going to add them up. And when we add them up, we get our mean. Okay? If we want to find the standard deviation, we got to first find the variance. So finding that variance is step 1. And that's found by doing this, where we're going to take the random variable value, we're going to subtract off the mean we just found, we're going to square that, and then we're going to take all of those values and multiply them by their probability for the proper x, and then add them up. Once you get the variance out, getting to the standard deviation is just taking the square root. Okay? All right, so we're going to take a look at finding the parameters for the first experiment of tossing 2 coins. So just to review, tossing 2 coins, we had an x and we had a p of x. Our x's were 0, 1, and 2. Our probabilities were 1/4, 1/2, 1/4, or if you prefer, 0.25, 0.50, 0.25. All right, so let's get started. The first one I'm going to find, the first value I'm going to calculate, is going to be our mean. Now the formula says it's the sum of every x times its associated p of x. So these are going to get multiplied, these are going to get multiplied, these are going to get multiplied, then we'll add them up, right? So that's going to be 0 times 1/4 plus 1 times 1/2 plus 2 times 1/4. 0 times 1/4 is 0. 1 times 1/2 is 1/2. 2 times 1/4 is going to give me 2/4. Okay. Adding those together, I get a 1. All right, so what does that tell me? What is that supposed to tell me that the mean is 1? Well, that tells me that if I sat down and played this experiment again and again and again and again and again, many times, flipping, recording, flipping, recording, flipping, recording, that sometimes I'm going to get no heads, sometimes I'm going to get 1 head, sometimes I'm going to get 2 head, but on average, if I added up all the heads I saw, divided by how many times I played the game, my average would be very, very close to 1. Right? Now, the reason why I say it's very, very close to 1 is because I would be doing statistics on a sample. This is the parameter for the population. So if I sat down and played this game for 8 hours and I found a mean of 0.98, I would look at that and go, yeah, that's really close to what it should be. Right. That's really close to 1. Or if I sat down and played this game for like 8 hours and I came up with a sample mean of 0.45, I would look at that and go, hey, wait a second. The mean's supposed to be 1 for the population. My sample mean, if I've done this enough, should be close to that. I got 0.45. Either I made a mistake in my math, or the other possibility is something's wrong with my coins. Okay. All right, so that's what's going on here, but we're only part of the way through. I need to turn this from a mean to the standard deviation ultimately, but I got to go through the variance, so I'm back to this formula. So the next step is to find the variance. So the variance, our population variance, is the summation of x minus the mu squared times the associated p of x. All right, so when x is 0, it's going to be 0 minus 1 times 1/4. When x is 1, it's going to be 1 minus 1 times 1/2. When x is 2, it's going to be 2 minus 1 times 1/4. Okay, clean that up a little bit. I've got negative 1/4 from this first bit. Oops, I forgot something. Oh, I forgot my squareds. Whoops-a-daisy. Okay. So negative 1 squared is positive 1, so I get positive 1/4 plus, well, that's going to be a 0 because 1 minus 1 is 0. And then down there, I got another 1/4, which gives me 0.5, 1/2. So I have a variance of 1/2, which means that my standard deviation is going to be the square root of 0.5. So I'm going to grab my calculator and go, hey, calculator, what's the square root of 0.5? And I get 0.71. We'll take it to 1 decimal or 2 decimal places, or 707, depending on how far I'm supposed to round it. Right. Now, I want to show you another way you could have done this. Stats, edit, 0, 1, 2, random variables in column 1, right? Probabilities in column 2, 0.25, 0.5, 0.25. Good so far? Right? So column 1 is my random variable. Column 2 are my probabilities. Now I'm going to ask my calculator to run one variable stats. My list will be my x's. My frequency list will be my probabilities. And then I'll calculate, and you'll see, okay, now here's where we have to be careful. My screen says x bar is 1, but I know that it's supposed to be mu is 1. So what's going on there? Remember, the calculator is dumb. So it doesn't know that this is a probability distribution. So we have to be smarter, and we have to say, hey, calculator, this is a probability distribution, so what you think is mean is actually population mean, not sample mean, right? But you will notice that it doesn't give a standard deviation for a sample. It only gives a standard deviation for the population mean. There's a reason behind that, but it's a little, okay, well, we'll go into it. I don't know if you remember way back when we had the standard deviation, the sample standard deviation formula set with the square root of the sum of x minus x bar squared divided by n minus 1. When the calculator is doing its math, it's calculating n down here by adding up the probabilities. And so if it adds up these probabilities right there, it's going to get a 1. And then when it does 1 minus 1, it gets 0. Now, if we change that formula to be the population standard deviation, that's just n. So we don't get a 0 in the denominator. So that's why it's leaving the SX out, the sample standard deviation, and only providing us with the population standard deviation. Now, there's one issue, there's one problem that we have with this, is it does not provide us with the variance. So if we needed the variance, we'd have to take that standard deviation and square it. So we'd have to take that 0.707106 blah, 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 and square it. Now you could either write that number down and then type it in and square it, or there's another way. If I touch the variables key, and if I go to statistics, I can get the standard deviation, and it knows that it's 0.707. So I could take that statistic, that population standard deviation, I could square it and get my variance if I needed it. Right? Okay, so now back to the problem. We were asked to find the population parameters for this example, and we found them. We found that mu was equal to 1. We found that the variance is 0.5, and the standard deviation is 0.71. All right. A little bit more. Here's another term that's going to show up in this section or in statistics. That is the expected value. The expected value is just the mean, just another way to say it. Okay? If you have an older instructor, they might not even use expected. They might talk about the expectation of the experiment. Okay? The expected value, the expectation. And basically what I'm asking is, hey, if I repeat this experiment a whole bunch of times, what should I expect the average outcome to be, the mean outcome to be? And it turns out exactly what we want it to turn out to. It turns out that the mean outcome is the mean of the probability distribution. It's just a different way to say it. So for the last example, you could say, for flipping 2 coins up here, you could say that the mean is 1, or you could say that the expected value of the random variable is 1. Right? And it really depends on the context of what you're talking about. We would use this context and talk about expected values if the point we were trying to drive home was that the mean of a long run of trials of the experiment would be 1. We would use this more if we were talking about making calculations on the probability distribution. Okay. All right, if you want interpretation, you could say mean number of heads is 1. The variance is 0.5 heads squared, and the standard deviation is 0.7 heads. Okay. To say it's the expected value means that, hey, if I collect data from a large number of trials of 2 coins, we should expect to get a mean somewhere really, really close to 1. All right, that range rule of thumb for significant values about significant low values and significant high values, right? So what I would like to do is I would like to talk about significant results. Significant low values are values that are well below the mean. How much? Well, 2 standard deviations or lower. What's a significantly high? Well, 2 standard deviations or higher. So any value that is between those, we say that those are not significantly low or significantly high. So if I wanted to determine whether or not the coins I had were good coins, or if the experiment was being run well, meaning flipped in such a way that they're flipping randomly, I could run the experiment, get an outcome, get a mean for a sample, and say, hey, if it's significantly low, then something's wrong with these coins. Or if it's significantly high, something's wrong with maybe not the coins, but the experiment. Right? All right, so for our next example, we're going to take a look at finding significant results using that range rule of thumb for the experiment tossing 5 coins. All right, so I'm going to pause the video and do some of the work off the screen for this one because I don't want to waste time having you watch me set things up. All right, so I'll be right back. Okay, so welcome back. That was quick. I set up our probability distribution when I'm tossing 5 coins. There are 32 different possible ways for the coins to land. If the random variable is going to count heads, then My possible outcomes are no heads, 1 out of 5 heads, 2 out of 5 heads, 3 out of 5 heads, 4 out of 5 heads, or all 5 coins land on heads. The probabilities associated with each of these. 1 way out of 32, 5 ways, 10 ways, 10 ways, 5 ways, 1 way out of 32. So those are all the possible outcomes. Right? Now, to get to that range rule for significantly high number of heads or significantly low number of heads, we need the mean and the standard deviation. Now, I could do this by hand with those formulas, but I'm lazy. I'm incredibly lazy, so I want to use technology. So I'm going to set this up again. I'm going to go Stats, Edit. I'm going to clear this stuff out because I don't need it anymore. That was a simple experiment of just 2 coins. Now I'm flipping 5 coins. So remember, in L1, I'm putting my X values, in this case, 0 through 5. In L2, I'm going to put my probabilities, so 1 32nd, 5 30-seconds, 10 30-seconds, 10 30-seconds, 5 30-seconds, and 1 30-seconds. You'll notice that I just type them in as fractions and let the calculator deal with the mess of making them into decimals. And then I'm going to say, oh, please, can you give me the stats on that? Now, since I used it last with L1, L2, it's holding on to that. You see how it still has L1 and L2 in here? Okay. Keep that in mind, because if you're moving back and forth between data sets, you have to make sure that this page looks like it should for the data set you got. We've got 2 list data here, so I need L1s and L2s. And so I calculate it, and I find that the mean number of heads, oh wait, no, that's wrong. It's not an X-bar. This is a probability distribution, so that means that our mean is actually a population parameter of 2.5. And that standard deviation down there of 1.12, if I want the variance, and I don't need the variance for this, but just for practice, if I want it, I got to square that number. So again, I'm going to go to Variables, under Stats, grab the population standard deviation and square it, and I get that the variance is 1.25. Again, like I said, I don't need it for this problem, but I wanted to find it. Okay. Now, I'm going to use those parameters to calculate the cutoffs for significantly low and significantly high. So significantly low is going to be any value of X that falls below our mean minus 2 standard deviations. Anything below 2.5 minus 2 times 1.12. So 2.5 minus 2 times 1.12. And so I get a significantly low cutoff of not 2.5, silly, it says 0.26. Which tells me that the only thing that could possibly happen that would be significantly low would be if I got no heads. That's significantly low. It shouldn't happen. Well, let me rephrase that. Not that it shouldn't happen, but it should be rare enough that I should wonder why it happened or how it happened. Right? Let's look at significantly high. Significantly high is going to be any value above the mean plus 2 times the standard deviation, so that's going to be 2.5 plus 2 times 1.12. So 2.5 plus 2 times 1.12, 4.74. So anything above 4.74, and I should look at it and go, well, the only thing that's above 4.74 is 5. So what does that tell me about this experiment of tossing 5 coins? Well, if I actually tossed it and got a random variable value of 0, that means it was tails, 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 all 5 tails. I should question that. I should take a moment and go, huh, should that have had, that's significantly a low number of heads. Okay. Or if I saw this happen, meaning the coins landed heads, 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 I should look at that and go, that's weird. Should that have happened? But if I saw this happen, 1 or 2 or 3 or 4, I would just go, yeah, that's cool. No worries there. Shouldn't bother with that. So the idea of significantly high or significantly low is things happen when I run experiments. Randomness comes into play. We get ranges of values, and I would go, should this happen? Shouldn't it happen? Now, if I want to go one step bigger, if I ran this experiment a bunch of times and I got an average of 0, I would say there's definitely something going on with these coins. Or if I got an average of 5. In fact, if I got an average of anything 0.26 or lower, I would say there's something going on with these coins. Or maybe there's something wrong with how I'm flipping them. Right? Flip side of that is if I got an average for running this experiment a bunch of times of anything greater than or equal to 4.74, I would also think something is wrong with this experiment. These shouldn't happen, right? Mathematically, this is a rare event just on its face. 1/32, that's like a 3% chance, 4% chance, somewhere in there. Same thing with getting all heads, 4% chance. Probably shouldn't see that very often. But one toss of the coins, yeah, that might happen. I still might question it, but it might happen. But definitely, if I run the experiment a bunch of times and I'm getting a really low average number, a really low mean number of heads, or if I run the experiment a bunch of times and I'm getting a really high mean number of heads, I'm going to start wondering what's going on with these coins. Anything between those two values, anything between 0.26 and 4.74 in that lovely little 0.26 to 4.74 range, I would just be like, okay, that's where we should be. That's where the math says this should become turning out to be. I'm okay with that. All right, let's look at how one might use this. All right, so here's our example. This is be a better, better. Oh, I don't want that. I wanted the highlighter. Here's the idea. Now, I'm going to preface this by saying that I do not condone gambling. I am not telling you that you should use your knowledge from stats to go to Vegas and become a gambler. But at the same time, I will acknowledge that people do gamble. So let's look at the layout of this. I'm in Vegas. I've got $5. I want to make a single bet at the Golden Nugget Casino in Las Vegas, and I'm going to play roulette. I have two choices. I can either bet it all on the number 7, which is betting at 35-1 odds, or I can bet on the color black, which is betting at 1-1 odds. Really quickly, what does 35-1 mean? It means I'm putting up $1 and they're putting up 35 times as much. So for every dollar I bet, if I win $35, but if I lose, they keep my dollar. Now, we said we were making a $5 bet. So that means that my $5, and let me grab my calculator so I don't make a mistake here. 5 times 35 means I'm looking at a possible $175 return on my investment. So I put $5 down. If I win, they hand me $175 additional dollars, so I get my $5 back too. Or if I lose, they just keep my $5. Similarly, that 1-to-1 means that if I'm betting $1, I'm winning $1. Or if I bet $5, they're putting up $5. Right? All right, so our job here is to figure out which one should we do? Which bet should we bet on? Which one has a higher expected value? Right? All right, so I'm going to split my page in two. On the left over here is going to be betting on number 7. On the right over here, we're going to bet on the color black. Right? I'm going to set up a lovely, little, beautiful probability distribution over here for this. I have two possible outcomes. I'm either going to win or I'm going to lose when I bet on the number 7. If I win, I am going to win $175. If I lose, I will lose $5. Did you notice that that lose is a negative $5 because that money's no longer mine? Right? The probability that I will win is 1 out of 38. The probability that I will lose is 37 out of 38. Okay. Now the expected value is just the mean of this distribution. Now again, I could calculate this by hand, but I'm not gonna. I'm gonna use my calculator. So let me bring my calculator back up. Stats, edit. I don't need all that stuff, so I'm gonna clear that out. Okay, so I'm clearing out my list. Remember, don't use the delete, use the clear. 175, -5. X is going in list 1. Probabilities in list 2. 1 out of 38. 37 out of 38. Stat, calculate, one variable stats, list 1, list 2, boom, 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 and I get a mean of -0.26. All right. Now, since this was money and this is money, that's also money. All right, let's interpret that. What does that tell me? Well, that tells me that if I went to Vegas and I sat down at the roulette table and I just kept plunking down $5 a pop on that number 7 and played this game again and again and again and again and again and again, many times, that on average, I would lose 26 cents. Now, I know at least one person is thinking, hey, you can't lose 26 cents. You either win $175 or you lose $5. Right. On one spin of the wheel, I can't lose 26 cents. But my average over a long run of the experiment would be to lose 26 cents. Okay, that tells me I shouldn't play that game. A negative expected value means they're always, on average, taking money from me. Now, it's not a lot of money, 26 cents per spin, but okay, they're still taking money from me. Maybe things would be better if we bet on black. So let's do that. All right, first things first, set up our probability distribution. We have X's. We have P of X's. We have two outcomes. We either win when we bet on black or we lose when we bet on black. If we win $5. If we lose our $5. The probability of winning is, let's see, on the roulette wheel, there are 38 spots. 2 are green. The rest are split evenly between black and red. So that's 36. So that's 18 black and 18 red. So the probability that I will win is 18 out of 38. The probability I will lose is then 20 out of 38. Now you might be saying, hey, where did 20 come from? I lose if it lands on red or green for a total of 20 different ways to lose. Right? My expected value, again, remember that's going to be the mean of this distribution. I need to calculate that, so I'm going to grab my calculator. Okay, clear, stat, 1. I need to clear those out. My outcomes are 5 or -5. My probabilities are 18 out of 38 or 20 out of 38. Okay. So you'll see here that it converted them to decimals for me, and I didn't even bother about reducing those fractions because don't care. Okay. Stat, calculate, one variable stats list one. That looks good. Calculate, wait, I get the same thing? I get negative 0.26 again? So if the expected values are the same, and if that means that if I play this game all day long, on average I lose 26 cents, does it matter whether I'm betting on a single number or whether I'm betting on a color? Maybe I should bet on green. Nope, expected value is still 0.26. Oh, I know in Vegas you can bet on 2 numbers at a time. Maybe I should do that. Nope, still 0.26. You can bet on 4, still 0.26 negative. They have set this game up and figured out all the payouts. So no matter how you play this game, they're going to take money from you, on average 26 cents for every $5 you bet. In general, for every $1 that you bet in Vegas, the casino keeps about 5 cents. The return on all the games, the expected value on most of the games is right around negative 5 cents. So they're keeping 5 cents of every dollar. Does that mean you shouldn't go to Vegas and play? Well, mathematically, it means you shouldn't go to Vegas and play. But if you look at it as entertainment and you can spend a couple hours there and only lose a few, I don't know, maybe $100, $200, and you can look at that as a cost for entertainment, maybe you could make it make sense that way. I mean, we pay to go see a movie. There's a cost for entertainment. We pay to go see a concert, or we pay to go do something with our friends that's fun. You know, if you pay to go to Topgolf, or you pay to go bowling, or whatever it is, so there's a cost for entertainment. And is this cost acceptable to you? Because if so, sure, then go do it. If you're going there thinking you're going to figure out a way to break the house and win money, no, not going to happen. They know the math better than we do. All right, that brings us to the end of section 5.1. I hope you had a good time, because I did. See you back here for section 5.2.